Hello, everyone. My name is Russ Balzer. I am Technical Director at World Auto Steel. And today we are going to do an overview of the UCSB World Auto Steel Automotive Energy and Greenhouse Gas Model. This is a full vehicle, full life cycle model, first authored by Dr. Roland Geyer back in 2007. We are now in version 5. As I said, this is a full vehicle model, and the idea of the model is to look at the effects of material substitution on the life cycle impact of a vehicle. The model calculates 27 main result values. These are 3 environmental indicators for each of 3 vehicles over 3 different life cycle stages. The 3 vehicles are a baseline vehicle that is specified by the user, and 2 contender vehicles, also user specified. The 3 environmental indicators are global warming potential over 100 years. This is given in kilograms of CO2 equivalent. Total primary energy requirements and fossil primary energy requirements, both given in megajoules. And the 3 life cycle stages used in the model are material production. And in this model, material production includes recycling of prompt scrap. So this is the scrap that is created in the production of the car or the parts of the car. And this is included in the material production stage because it happens early in the life cycle of the car. Second vehicle life cycle stage is vehicle use. And the third is end-of-life material recycling. As the model has been developed, we have really kept 4 main points of philosophy in mind. The first is that Dr. Geyer wanted a complete separation of the computational structure from the parameter values. So the computational structure, essentially the methodology of the model, is completely separate from the parameter values. This allowed the computational structure by itself to be peer-reviewed, and in automotive LCA, there is broad agreement as to methodology, as to how the computations are done, and most of the remaining disagreement is on parameter values. So this was the main reason for separating these 2. And that leads into point number 2, the complete transparency of both the computational structure and the parameter values. This is one reason that the model continues to be in Microsoft Excel. This allows all of the computations as well as all the parameters to be seen by the user. Nothing in the model is hidden, and nothing in the model is locked. So as you will see when we look at the model, there are default parameter values for all of the parameters, but any of those values can be changed by the user if they have what they believe is a more appropriate value. The third point, has always been kept in mind during the development of this model is a balance between comprehensiveness and simplicity. As the model has evolved from a strictly material substitution model towards a comprehensive vehicle model, we want to maintain a certain ease of use. The model is used not only for case studies of different automotive material substitutions, but also as a teaching tool about LCA in general and about automotive LCA in particular. And Dr. Geyer wanted, again, while maintaining a comprehensive model, to make it usable and understandable by people who are perhaps not LCA experts or are not perhaps automotive experts. And finally, in any modeling, and in LCA modeling in particular, sensitivity and scenario analysis are important. Another reason to continue using Microsoft Excel is it makes these very easy to do. So whenever you're doing anything, any sort of modeling, it's important to think about sensitivity. So when I'm making assumptions about the parameter values that I use, or perhaps about the methodological choices that I make, I need to be able to understand how the results of the model change as those assumptions may change. I also need to be able to look at how robust are the results. If I select a certain set of parameter values and I get a certain result, is that result still appropriate for a wide range of parameter values around the value that I chose, or maybe only a very narrow range? So it's very important. And scenario analysis as well helps with the usability of the model, to be able to examine simultaneously several different scenarios. So that's a brief introduction. Let's take a look at the model itself. So the model is divided up into several tabs, some of them for data input, some of them for data reporting, and some of them for computation. This is the primary data input page. Here you can input some of the global parameter values that will be applicable to all of the contender vehicles. We talked about comprehensiveness a little while ago. The UCSB model allows you to model 7 different powertrains across a total of actually 5 different vehicle classes. There are these 3 vehicle classes for internal combustion engines, and for battery electric and hybrid vehicles, there are 2 additional classes based on future steel vehicle. The model allows you to select from 4 different driving cycles. And a variety of different biofuel as well as electric charging sources, each of which, of course, has a different environmental impact attached to it. The section we see here allows you to generate the bill of materials for your 3 vehicles using a standard material substitution method. This is, I take out one material and I replace it with a certain amount of another material, the model then calculates the final bill of materials for each of those contenders. If you already know the bill of materials of your vehicles, the model also gives you the option to enter those directly on the bill of materials entry tab. In the interest, as we said, of ease of use, in version 5, Dr. Geyer has separated out some of the more expert data inputs onto a separate page. So non-expert users do not need to change anything on this page, but expert users who may, in some cases, have more appropriate parameter values can change those here. Those are things like your baseline material composition, some battery information for electrified vehicles, origin, either by region or by process of the manufacturer of some of the materials, as well as how credits for recycling are allocated to each contender by each material. Also on this page is some information that comes from Argonne National Lab's GREET model about plastics and fluids production. Again, not necessary to change anything here, but an expert user can change any of these values if they believe that they have a more appropriate value they want to use. Talked earlier about scenario analysis. So you may have noticed on both the data input and the bill of materials entry tab, these record scenario buttons. These simply allow you to choose a set of parameter values and record the results of that scenario. You can record up to 3 scenarios, and this allows you to examine them, the results side by side. The material flow tab calculates the amount of both primary and secondary material that must be produced in order to arrive at the vehicle compositions that we calculated earlier. And also includes important material flow parameters like scrap input to production of the material and yields from forming and recycling scrap recovery, as well as information necessary to determine the overall scrap balance of the system that is being studied. The use phase tab is just that. It shows all of the calculations for the energy demand and therefore the fuel demand for the baseline and each of the contender vehicles. The recycling tab is much like the material flow tab, except this time we are looking at scrap that is generated in each material, in each phase, both prompt scrap and end-of-life scrap for each of the vehicles. The ES tab is energy demand and energy savings. So here we find the default values for the energy demand of the baseline value or the baseline vehicle, as well as energy savings values, both with and without powertrain resizing. And again, as you can see, these are for all of our combinations of different powertrains and different vehicle classes and driving cycles. All of these values are based on the Malin-Geyer powertrain model. This is another Excel model co-authored by Dr. Geyer and Dr. Donald Malin from the University of Michigan. Again, if the user believes they have more appropriate values, if you are studying a particular vehicle, for example, and you already know the energy demand of that vehicle, you can change that. The user can input their more appropriate value. So the LCA calculations tab, again, is pretty self-explanatory. Up till now, the model really has been calculating what we call activity levels. So the activity level is the amount of each material that goes through a given process, whether that process is material production, material finishing. In the case of fuels, it could be the production of the fuel or the combustion of the fuel. So all of the tabs that we've looked at up to now have gone to calculating these activity levels here for the baseline and for each of the contenders. Here on the LCA calculations page, those activity levels are married with the database of environmental impacts. Here we see our three environmental indicators: total energy, fossil energy, and greenhouse gas emissions. Is a simple multiplication, the impact per unit times the number of units, which is the activity level, gives you, for each of the three contenders, the impact of that material or of that activity for each of the three contender vehicles. And then it is simply a matter of summing these up for each of the three life cycle stages. Before we leave this page, this is also where we find the sources for the data. As with any model, the data that you put into it is critical. So in this case, this is where the impact data comes from, these in the blue columns here. Most of the impact data comes from the Gabi database, which we will talk about here in just a second. We'll take a quick look at the results tab. So as I said, all of the environmental impacts are totaled up by their appropriate life cycle phase. And this is how results are reported. So we had two ways. One sort of more time-based. It's of course a vehicle, so it's mileage-based, beginning at the production phase and then going through the life of the vehicle and then reflecting at the end of life, any end of life recycling credit that the vehicle may get. The results are also shown in a column chart here and given in the table with all of the comparisons. So the baseline to contender 1 comparison, a baseline to contender 2 comparison, and a contender 1 to contender 2 comparison. And these results are given in the same format for all three of our environmental indicators. Here we have greenhouse gas emissions, total energy requirements, and fossil energy requirements. So I mentioned here, as we were talking about data sources, that the data comes largely from the Gabi database. So the Gabi database is what is called a life cycle inventory database. It's developed and is maintained by a German company called ThinkStep. And the important thing about the Gabi database is that it is a full life cycle inventory database. Normally, when we are generating this data, and we're concerned, as most people primarily are, with CO2, when you generate this impact data, you really only need to look at inputs and outputs to that process that affect global warming potential, and also in our cases, energy. Several years ago, in talking with Dr. Geyer, his opinion was maybe we should look beyond just global warming potential and energy. It's true that those are the two things that most people are concerned about. But if we really want to properly do LCA, LCA is not just about looking for trade-offs between life cycle stages, though that is a critical part. But another critical part of LCA is looking at trade-offs between environmental impacts. Just as I do not want to make a change in one phase of the vehicle that may have an unintended effect in another phase, for example, reducing my use phase emissions, but increasing my production phase emissions, I also want to make sure that when I am making changes to reduce a particular environmental impact, I don't have an unintended effect in another environmental impact. For example, if I'm working to reduce my global warming potential impact, I want to make sure I'm minimizing any unintended effects, for example, in the creation of smog. And LCA allows us to do this. And in fact, it allows us to do this by connecting to the full LCI data in the Gabi database. We do this through a tool that we've been developing in conjunction with Dr. Geyer over the last several years that we call Auto LCA. Auto LCA allows us now, using the UCSB methodology, to look at a whole range of environmental indicators beyond global warming potential and energy demand. An example of some of those are, we'll just look at this list here from the Tracy impact tool. Now we can look at environmental indicators in addition to global warming potential. We're still looking at global warming potential and energy demand. Now we can look at a whole host of other impact indicators like acidification, toxicity, eutrophication, again, ozone depletion, things like smog. And we can look at these things over the same three life cycle categories. So this gives us a much broader picture of what the real environmental impact of the kinds of material substitutions that we look at. We go back to the presentation here very briefly, talk a little bit more about Auto LCA. So again, we said this is the integration of the UCSB methodology with the Gabi database. And there are several benefits actually to connection with the Gabi data sets. Because the data is all gathered essentially by the same group of people, there is an element of standardization to it, which is very helpful in understanding, in making good comparisons. It's very helpful to understand that the data gathered and that you're using has, for example, similar boundary conditions. As I mentioned, it is full LCI data, which allows us to look at all of these different environmental impacts. And Gabi is a very well-known database. It's used all over the world. Gabi contains thousands of different data sets on many, many different materials and different processes. The database is upgraded annually. And as I said, having the database as a sort of clearinghouse means that there is some standardization of the methods and the boundaries across the data sets. There are several ways to examine different, the impact in different environmental indicators. These are called impact assessment tools. We have several impact assessments. There are many impact assessment tools available in the Gabi database. We simplify, for the purposes of Auto LCA, to just a couple. One of those is the current list of environmental impacts that is recommended by the European Product Environmental Footprint. Another is what is called the TRACY. The list we looked at earlier is from what is called the TRACY Environmental Impact Assessment Tool that was developed by the US EPA. And we are in the process of adding another impact assessment tool called CML from the University of Leiden. As I said, Gabi was used globally, and this use includes almost all the major OEMs all over the world. Any OEMs that are doing life cycle assessment are almost all in some form or another using the Gabi database. So this is very helpful that we are sort of speaking the same language across the whole automotive sector. Another good thing about using the Gabi database is that ThinkStep has a web portal that they call Envision. This allows us to host the Auto LCA model, and it allows access to that model through this Envision web portal. So this means users of Auto LCA do not necessarily have to have a full license to Gabi, but they can still use, can still have access to the Gabi model through this interface. And in version 5 of the model, we have really streamlined this process. The web portal allows you to upload a parameter value sheet that looks like this. It's designed that you can upload this sheet in Excel format. So what this means is in version 5 now we have integrated this Envision parameter sheet right into the model. So now instead of doing your calculations in the Excel model and then going to the web portal and entering all your parameters again, you can be using the model, calculate your CO2 and energy, your global warming potential and energy demand values. And if you want to look then at impacts beyond those, you merely go to the web portal and you can upload the entire file, the same model file that you have been using before. And it makes it much easier and much more streamlined. It is slightly more complicated to get the results, but Envision again allows you to copy the result tables. These result tables will generate automatically in Envision. And you can merely copy them down and paste them here into the Auto LCA results tab in the UCSB model. And all of the charts will automatically populate. So it's a very much easier, very much more streamlined way to get all of your additional environmental impact results using only the one Excel model file. So that's it for a quick overview of the UCSB model version 5, including Auto LCA. The model is available for free download at our website, worldautosteel.org. So you can go there, you can find the UCSB model, some of our other models that we make publicly available, as well as a lot of great material on LCA and on automotive LCA and some of the other work we've been doing at World Auto Steel. I appreciate your attention. If you have any additional questions, please feel free to contact me. I would be more than happy to answer any questions you might have. Thank you very much.